Hey guys, welcome back for another chemistry lesson. Today we're going to talk about ideal gases versus non-ideal gases, and we're going to put everything that we've talked about already together. So let's talk about the ideal gas law. So the relationships that we have discussed so far in the simple gas laws can be combined into one single law that encompasses all of them. So we've got the volume and pressure relationship, that's Boyle's law. We've got Charles' law, which relates volume and temperature. We've got Avogadro's law that relates volume and the number of moles. And so we have this relationship between volume, number of moles, temperature, pressure, all of that together. So by combining these gas laws, we can write a general equation, which we call the ideal gas law. And it involves R, which is the gas constant. And the value of R is different depending on our units that we use for pressure and volume, mainly the one about pressure. So the other gas laws are found in the ideal gas law if two of our variables are kept constant. And it allows us to find one variable if we know all of the other three. So this is what you will see in the ideal gas law. The most popular way to write it is PV equals nRT. I like to call it PivNert. You can also rearrange it for any of these variables to sort of give you what you need to solve. And so in this case, we've got volume, but you can arrange it for anything that you need. So here, if we keep N and T constant, we end up with Boyle's law. Same law, keep N and P constant, Charles' law. Here, keep P and T constant, Avogadro's law. So all three of these laws are built into that one gas law problem. So one thing that you do need to know, because it is used a lot with gases, is standard conditions. Our standard conditions are very important because the volume of the gas that we're talking about will vary depending on the pressure and temperature. And so in order to sort of have a standard temperature and pressure that we record information at and present information at, they set a value for these things that experimentally you have to record at. So we call these standard conditions. You may also see them called STP, which stands for standard temperature and pressure. Standard pressure is 1 atmosphere. Standard temperature is 0 degrees Celsius or 273 Kelvin. Now, the molar volume is also something that you need to be familiar with. It is the volume occupied by 1 mole of a substance at standard temperature and pressure. So again, 273 Kelvin, 1 atmosphere, right? So we can solve for that by plugging in 1 mole, 1 atmosphere, 273 Kelvin, and then the appropriate gas constant value. And the gas constant values are reference numbers, so you should be able to find them. You should be comfortable with using them. You probably also should memorize them. But if we plug all of this in, we get 22.4. Hopefully that number sounds familiar to you because it is something that when we're doing mole calculations, this is a value that we can use. Now, solving the ideal gas equation gives us 22.4 liters. This is for 6.022 times 10 to the 23rd molecules of gas or atoms of gas. Notice, it does not matter what that gas is. So here, you can see helium, 1 mole at STP is 22.4 liters. Xenon, 1 mole at STP, 22.4 liters. Methane, 1 mole at STP, 22.4 liters. It does not matter what it is. So again, this is our molar volume, and it is important that you know that even though we're talking about how it doesn't matter what the substance is for the molar volume, it is important that you recognize that the mass will be different because they're different substances. So 1 mole of helium does not weigh the same as 1 mole of xenon. We've talked about that to the point of exhaustion in the stoichiometry stuff that we've gone over. But it's important to know because we do calculate density of gases at STP. And this is where the mass to volume ratio comes through. So you've hopefully seen at this point that density is equal to mass over volume. Density of gases are usually given in grams per liter. For solids, that's not generally the case. It's usually grams per cubic centimeter or per milliliter for liquids. But for gases, it's grams per liter, right? So we already know what the mass of 1 mole is. That's the molar mass. We use this so much. But now we know what the volume of that same 1 mole is, 22.4 liters. So the density of a gas at STP can be calculated by doing the molar mass divided by molar volume. So, for example, here we have helium. So helium weighs 4 grams per mole, and the molar volume is 22.4 liters, which gives us a density of 0.179 grams per liter at standard temperature and pressure. Nitrogen is a much heavier gas, so it's 28.02 grams per mole. In that same 22.4 liters means that we have a much higher density for our nitrogen gas at that same volume and temperature and pressure. Now, these are all important things that you need to know. We can relate this back and actually substitute in so that we can look at the ideal gas law with our density in it. So here we've got our density, our molar mass, and so it's been sort of substituted in this way. So if you ever need to figure out your density based on, or your molar mass based on a density using the ideal gas law, this would be the formula that you would use. Okay, so one method that we can use to determine the molar mass of an unknown substance is to heat a sample until it becomes a gas. We measure the temperature, the pressure, and the volume of that gas that we have created, and then we can figure out what the molar mass is, again, using that previous equation that I showed you. So, in reactions that involve reactants or products, we usually specify the amount of gas in terms of its volume at a given temperature and pressure. And unfortunately, what that means is we're going to have to do some math before we can do stoichiometry, because our stoichiometry has to do with moles and mole ratios and all of that. So whenever we have temperature and pressure of our gas, we can, in a volume, we can then bring it here and solve. Sorry, that totally caught me mid-yawn. We can bring it into this equation, rearrange for a number of moles, and solve. And then we can take that into our stoichiometry calculations. So, when gases are at standard temperature and pressure, we use the molar identity, 1 mole equals 22.4 liters. Our pressures could also be partial pressures. And we have this sort of general concept map here, right? Normally we have our mass of whatever gas it is. We convert that to moles. We then get to moles of whatever we're looking for and convert that to mass. In this case, when we're talking about gases, we use the values that were given, pressure, volume, temperature. Then we can use the ideal gas law to convert it to moles. And then we do the same stoichiometry to get the amount in moles, and then we can go back to any of our gas thingies, whichever of these variables we need, as need be. Now, the kinetic molecular theory is a quantitative model that describes this relationship that we talk about in the ideal gas law, right? And just reminder, our pressure we get by looking at the total force on the walls of the container divided by the area of those walls of the container. And this pressure comes from the constant motion of our gas particles. So keeping that in mind, this is what we call a Boltzmann distribution. This is looking at the average kinetic energy of gas molecules, and this is totally dependent on the mass and velocity, right? So this is a graph that shows us various gases at the same temperature based on their mass and their velocity, right? So according to this equation, this is a physics thing, our average kinetic energy is related to the number of particles we're talking about, and then our mass and our velocity. So the heavier a gas is, the slower it can be moving to have the same amount of energy as a lighter gas. So think about it like a person, right? If I have a, sumo wrestler that's walking and bumps into me, right? They're just walking, but they have such big mass that force of contact is gonna, bump me out of the way pretty good, right? Think about like a 5-year-old. How fast is that 5-year-old gonna have to be moving to hit me with the same impact as that sumo wrestler just walking by me? It's the same thing with our gases, right? So gases in the same container have the same temperature, so the same average kinetic energy. That does not mean they're moving at the same speed. There's going to be a distribution, and then we have an average speed, which gives us our average kinetic energy, average temperature. So oxygen here is the heaviest gas on this graph here. So we have a large number of oxygen molecules moving at, a little under 400 meters per second. And then in either direction, we have fewer and fewer and fewer as we go down our little graph here, right? Same average kinetic energy, the lighter gas of nitrogen, on average, they're going to be moving a little faster. Water is even lighter than that. They're going to be moving a little faster. Helium is even lighter than that. It's going to be moving a little faster. And then the lightest on this graph is our hydrogen, which is going to be moving even faster. So the faster the average velocity, the wider and shorter the piece of the graph is going to be, because we're going to have a wider distribution of potential velocities at which these molecules are going to be moving. The only way for our gas particles to have different masses and the same average kinetic energy is for their average velocities to differ, which is what we see here, with our x-axis being our molecular velocity. Alright, so as the temperature of a gas sample increases, the velocity distribution of the molecules shifts towards higher velocity, which hopefully makes sense. Just think about what happens when you put a pot of water on the stove, right? It looks dead still, and then you heat it up, and even before it gets boiling, you can see the water moving around. Same thing, but with gas particles. So this distribution spreads out, and we get more molecules with faster speeds. So here we can see this is nitrogen. At 273 Kelvin, we have a very large number of nitrogen molecules moving at this low speed, and then a fairly narrow distribution of potential speeds. Right? The warmer we get, 1,000 Kelvin versus 2,000 Kelvin, the higher the molecular velocity, right? So we're going from peak here to peak there-ish to peak there-ish. And we have this wider distribution, so shorter, fatter distribution curve. Okay, so let's talk about diffusion and effusion because this is directly related to that molecular motion. So diffusion is the process of molecules spreading out from high concentration to low concentration. This is what you experience, like, let's say in the corner of my office over that way, I break a bottle of perfume, right? Those perfume molecules get up into the air. They're very highly concentrated over there, right? I'm going to smell that perfume in this corner of my office or even out into the hallway less strongly, but I'm still going to smell them out there because the particles have been going from an area of high concentration where I broke the bottle to an area of low concentration where I did not. That is diffusion. The process of effusion is when our gas particles escape through a small hole into a vacuum. So if my office was a vacuum and I broke the perfume in a box and I had like a little pinhole, eventually particles, even though they're moving about randomly, eventually they're going to hit that hole and be able to leave to go out into this vacuum. That is effusion. So for gases at the same temperature, this means the rate of gas movement is inversely proportional to the square root of its molar mass. And this is what effusion looks like. This is the reality of how we sort of measure these things and look at them in a lab. We have this high concentration here, and then our vacuum, and then this small pinhole. All right, so all of this has been about ideal gases, and while we can make a lot of assumptions about real gases and be correct about them by looking at them as ideal gases, real gases are not ideal. That they don't actually behave like this in real life. So the two conditions where real gases are most different from ideal gases are at high pressure and low temperature. So you can see here, the ideal gas has a molar volume of 22.41. While this is close, these are not at all 22.41 all the way across. That's just not what it is. But it gets more and more different the higher the pressure or the lower the temperature. So the ideal gas law assumes no attraction between gas molecules, which is mostly true until, I just gave a thumbs up, which is mostly true until they run into each other. Gas particles don't take up space. According to the kinetic molecular theory, they do. It's just not a whole lot of space, especially compared to the amount of empty space in between them. And then, because of these two assumptions, low temperatures and high pressures do not allow this to be true. Because what we're doing is, remember I said there's no attraction between gas molecules until they run into each other. Well, at low temperature and high pressure, they run into each other a lot more, so it actually matters. And then likewise, they don't take up a whole lot of space, but when we have low temperature and high pressure, what that does is it decreases the total volume of our gas. And when all of our gas takes up this amount of space, and the gas particles, even though they're tiny, still take up about this amount of space, well, now that volume matters. So let's look at that. So at low pressures, the molar volume of argon in this example is nearly identical to an ideal gas. But as our pressure increases, the molar volume of argon becomes greater than that of the ideal gas. And that's because these argon atoms, there was so much empty space that the volume of the atom itself didn't really matter. But whenever we have this small space because of our higher pressure. Now, look how much of that space is taken up by those dots. Now, obviously, this is an exaggeration, but clearly, they take up a lot more space. So, our volume is going to be different. Because real molecules take up space, the molar volume of a real gas is actually a little larger than predicted by the ideal gas law at high pressures. Because we have the space assumed plus whatever that minute volume of our gas particles is. So, in 1873, Johannes van der Waals, I have no idea if I pronounced that right, I'm not Dutch, identified the ideal gas equation, and then, he modified it in a way that accounts for the real gas behavior at high pressure. So, he has this little addition here for the volume component. Right, so the molecular volume makes the real volume larger than the ideal gas law would predict. So he accounted for the molecular volume using what he called a van der Waals constant. And it's different for every gas because molecules are different sizes, right? So if we're talking about a hydrogen molecule versus a gigantic xenon atom, right? Totally different volumes, so their impact is going to be different. And then the other difference, at high temperature, the pressures of the gases are nearly identical to that of an ideal gas. At lower temperatures, the pressure of the gases is actually less than that of an ideal gas, right? So the reason for this is, at lower temperatures, our gas atoms and molecules are actually spending more time interacting with each other and with the walls, interacting with each other than with the walls, And so what that does is, if they're stuck in here interacting with each other, being attracted to each other because they just are, they're spending less time out here bouncing against the walls of their containers, right? So he again modified the ideal gas equation to account for the fact that molecules actually are attracted to each other, even though in gases it makes less of a difference under normal conditions. So we have this additional piece here to account for the change in pressure from those interactions. So A here is another van der Waals constant, and it's different for every gas molecule because these molecules have different strengths of attraction for each other, depending on what they are. If they're polar molecules, it's going to be a lot bigger attraction than nonpolar molecules, for example. So it totally depends on what the substance is. So we have this really complicated equation, which is the van der Waals equation that we use for real gases, with the correction for attractive forces and the correction for molecule volume. And so we have these reference values for our gases where we have A and B values, and you plug those in and it's just a much more complex calculation. So we can plot the ratio of PV over RT versus P for 1 mole of gas, and it'll show you the difference between real and ideal gases. And what we see is that at low pressures, our ratio is generally lower than it would be for an ideal gas, which shows us that the most important factor is intermolecular attractions at this low pressure. And then at high pressures, this ratio is generally higher than ideal for high pressures, meaning that the most important factor at high pressures is the molecular volume. So what we get is a graph that looks like this. As you can see here, we've got sort of a dip at low pressure, and then high pressure, it goes and skyrockets, which just shows us, again, down here, the intermolecular attractions are the most important when we have low pressure, and then when we get up to high pressure, it's the volume of the molecules that makes the biggest difference.